We're still using matrix methods to solve systems of differential equations. And we did having real and distinct eigenvalues and having repeated eigenvalues, but where you got a full set of linearly independent eigenvectors. And now we'll cover the case of complex eigenvalues. When they're complex, we're going to write them this way. We'll call it alpha plus I beta. The eigenvalues will always come as complex conjugate pairs as long as the A matrix is all real. And the eigenvectors will also come in corresponding complex conjugate pairs. So these would be the solutions, but they're going to have complexities up here in the exponents, and the eigenvectors themselves will be complex. So we have all real problems to begin with. We expect real solutions, so we don't do this like we did before. What we did, and if you want the derivation, email me and I'll give you my lecture notes. But we use Euler's equation, Euler's formula, and we come up with basically formulas based off the alpha and beta. Here's our two particular solutions, x1 and x2. E1 is the real part of the K1 eigenvector. B2 is the imaginary part of the K1 eigenvector. We don't even need lambda 2 or K2, okay? Everything is based on alpha, beta, and the K. So B is a little vector, get it from K1. B2 is a vector, we get it from K1. The alphas are these exponents out here, and the betas are basically the frequency of these sinusoids, cosine and sines. Either cosine beta t or sine beta t. Anyway, these would be written on a formula sheet when you do homework or an exam. At least I didn't require my students to memorize them. So here's how you write the general solution. You could write the x1 and x2 this way and then say, well, here's the general solution. And I made my students do that, by the way. They couldn't just write these and be done with it. They had to at least write this. And some students were not making the connection. Simple transition, it's just the general solution is just a linear combination of these two particular solutions. So here's an example. We have two differential equations and two unknowns, first order. So you can write down what the A is, right? 6 minus 1, 5, 2, right? Here's our A. Do our eigenvalue problem. We get a quadratic. I could either do my little complete the square trick, which I have to find my alpha and beta, or use the quadratic formula. Either way, here's what eigenvalue is. So alpha equals 4 and beta equals 1. Let's see, okay, let's find the K1. I only need to find K1. Let's find that eigenvector. Here's the eigenvalue. So I'm subtracting 4 plus I off of 6. I have 2 minus I, and this will be minus 2 minus I. The rest of it's the same. And if you use my trick, it'll be this over minus that, or vice versa. I could minus this over this. There you go. There's our eigenvector. 1 over 2 minus I. Okay. What is B sub 1 in our little formula? B1 and B2. B1 is the real part of that eigenvector. B2 is the imaginary part of that eigenvector. We're just going to plug and chug, put them in these formulas. real part of this eigenvector is 1, 2. Imaginary part of this eigenvector is 0, minus 1. Got it? Can you do that? Do that, you got it made. So now we just put it into the formula. Here's, I guess, B1, here's B2, here's B2, here's B1. We just go back to our formula sheet and do what it says. Beta was 1 and alpha was 4. I could write it this way or I could write it that way. So the total solution, I could write it this way. And on exams, I was happy with, if you show me what x, the two x, what x's are, x of 1 and x of 2, and then say this is the general solution, linear combination of them, that was good enough for me. You didn't have to write this out. It's sort of time consuming in an exam. Although it seems very simple to me, some students could not go from here to the general solution. Anyway. You could have another legitimate answer and look entirely different to you. Just trying to compare your answer to the solution manual or what's in the back of the book or something like that. I could have said K1 was 2 plus I over 5. And I'd end up getting a different looking answer, but it is still a legitimate answer. These arbitrary constants, C1 and C2, absorb the differences. Almost the last subject, diagonalization. If you can diagonalize A, we talked about diagonalization in a previous recording just for matrices. Now that it comes to systems of equations, solving this system of equations, what if I find another variable y, P inverse x, where P is the diagonalizing matrix. X will be py, x prime equals py prime, a little bit of algebra. And I end up with this differential equation in terms of the new variable y. Y is actually a vector of variables. D, remember, was the diagonal matrix made up where the diagonal terms were the eigenvalues. That means y is this, which means we've decoupled them from each other. Y1 does not in any way depend on any of the other y's. Same with Y2 through Yn. I just have n coupled differential equations, and it will have this solution. None of them depend on the others. Take an example. Here's our original system. Here's our eigenvalues. We already did this problem. I could write, if I said, okay, write the decoupled system. I'd either write this or that. Either one would be correct format in my class. This is the decoupled system. All you needed was the eigenvalues. Y prime equals its diagonal matrix where the diagonal elements are the eigenvalues. Okay, write the solution to the decoupled system. This. First one has to match that eigenvalue, so it's e to the 1t and e to the minus t. Order has to match. So I could do all that with just the eigenvalues. I could write the decoupled system equation and the decoupled solution. If I want the solution for x, I have to do this matrix multiply. Remember, x was p times y. And to get p, I needed the eigenvectors. We did that problem before. It's not a fun problem, but if I do have the eigenvectors, I can write p. Then I could do this matrix multiply pretty easily. and there is my solution to x. This is not really a more efficient way to get the solution to x. It's not really for that purpose. I think the purpose is to decouple the variables and get some insight into that. You just kind of cleaned up your problem by putting it in another dimension. What you did was a linear transformation of variable x, one that's decoupled. Anywho, another example, I'll go through it super quick. Part A is just write decoupled system equation in Y. And all we need to do for that is get the eigenvalues. Same for B, write the solution to Y, decoupled system. For A and B, we only need to find the eigenvalues. Did all that before, you get a quadratic, -4 and 7. So here's the decoupled system equation. All I need is to write a diagonal matrix with those two eigenvalues on the diagonals. And the solution is coefficient equals e to the -4t, another one with e to the 7t. Order has to match this. To find x, I have to find the eigenvectors. I'm not going to go through that. Then I come up with the speed by its columns are these eigenvectors. 2 minus 3 there, 1 there. This is my x. Multiply it out, it's this. Anyway, that's diagonalization. We cover it because it's so easy once the hard work is all in the eigenvalue problem. One last little chart to wrap up some of this. What do the eigenvalues mean? You might hear somebody say the eigenvalues of a system. Well, they tell you the behavior of the system, or at least parts of the system. The solution to the whole problem is going to be a linear combination of terms. And those terms are going to be some kind of exponent or some kind of oscillation in an exponential envelope. If your eigenvalue is real and less than 0, it's going to be shrinking like this, shrinking exponential envelope, at least that term, the term corresponding to that eigenvalue. If the eigenvalue is real and greater than 0, it's going to be a growing exponential. Or exactly equal to 0. If your eigenvalue is complex and the real part is less than 0, it will be oscillation at the frequency beta, radians per second, inside a shrinking envelope because of the alpha. If alpha is greater than 0, it will be a growing exponential. Inside, it will be oscillation beta. So the eigenvalues tell you quite a bit about the behavior of the system. Here's such terms. And that, boys and girls, ends my entire module 2, which is all about matrices, at least the parts I teach in engineering math.